Hi, thanks for joining us for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. Over time, land uses and nutrient management practices around a particular water body change, and these changes impact how phosphorus is delivered from land to water. Spanning 150 years, the River Thames in the UK boasts the longest known continuous data set of phosphorus measurements, along with other data. This provides an unusual opportunity to study the long-term impacts of land use and nutrient management practice changes. Today's guest, Dr. Helen Jarvie of the University of Waterloo, discusses how her team leveraged these data to better understand the Thames's nutrient dynamics and how new threats pose challenges to mitigating harmful algal blooms. Well, thank you, Helen, for joining us for Phosphorus Science Now. This is a really excellent paper, and I'm very interested to hear about the work you've done. Can you first introduce your collaborators and tell us where you got your funding for this research?
Okay, well, thank you, Matt. Thanks for the opportunity to talk and share some information about this research. So this research was done in collaboration with colleagues in the UK, Professors Tim Burt and Fred Worrell at the University of Durham, and Nicholas Howden at the University of Bristol. And the work, I'd like to acknowledge funding from the NSERC, the Natural Sciences and Engineering Research Council of Canada. So the paper explores river eutrophication trajectories through the lens of a really quite unique 150-year water quality data set for the River Thames in England. It's the world's longest water quality record, and I'll talk through the paper, but also at the end, there's a photograph that you'll see on the slide. Tell you a little bit about how this work has also inspired a new musical composition, Echoes of the Thames. And we think it's likely that this is the first time that river phosphorus loads have been translated into classical music. Okay, so our story begins back in the summer of 1858, and a notorious event in British history, the Great Stink, when the City of London and the Houses of Parliament came to a standstill as a result of the overwhelming stench from untreated sewage that was flowing unimpeded into the tidal reaches of the River Thames from a rapidly growing urban population. Now, the widespread adoption of the water closet in the 1800s meant that human waste was no longer collecting in cesspools, but it was being transmitted from houses via sewers directly into the River Thames. And although this improved living conditions in homes, it led to heavy contamination of the tidal reaches of the River Thames in London. And obviously, in addition to the unpleasant stench of putrefying sewage, waterborne diseases like cholera were rife. And this was because the tidal River Thames at the time was the main source of London's drinking water supply. So action had to be taken to address the troubled waters of this really iconic river, and to develop a cleaner supply of drinking water for the population of London. And as part of this, Bazalgette's pioneering sewage system was developed to funnel and take the sewage away from London and discharge it further downstream into the Thames estuary to the east of London. But at the same time, new water intakes and water treatment plants were developed to the west of London, upstream of the tidal limit at Teddington, to secure a clean drinking water source. And with those developments in new water sources came a requirement to measure the water quality. And so water quality monitoring of the River Thames at Teddington began 10 years after the Great Stink in 1868 and has continued to the present day, making it the longest continuous water quality record in the world. And we have uninterrupted monthly data going back 150 years for chloride, for nitrates and biological oxygen demand, amongst some other determinants as well. And we have 90 years of data for phosphorus, total reactive phosphorus, and silica, which we use as a surrogate for diatom growth. So going back to 1836 to 1936. So we also have accompanying 150 years of river flow, meteorological data, land use, and census records. And these historical water quality and land use records were painstakingly transcribed and digitized from archival materials by colleague Nicholas Howden from materials in the British Library before being harmonized and compiled with meteorological and flow records. The first graph shows the population of the Thames watershed going back to 1868 and the concentrations of chloride. And this is where urbanisation plays a big part in the water quality history of the Thames over the last 150 years. We use chloride as a conservative tracer of sewage, and it closely tracks population growth, reflecting increasing urban contamination from sewage and urban runoff. The time series here of biological oxygen demand up until the mid-1960s also generally tracks population, but chloride and BOD diverge after 1965, reflecting the expansion in activated sludge treatment, removing organic materials from the final effluent and improving the quality and the health of the River Thames. And because chloride is chemically conservative, river chloride concentrations weren't affected by changes in wastewater treatment, whereas the BOD was. And then when we add in our biological, from the biological oxygen demand to total reactive phosphorus, we can see we have a shorter time series. Again, phosphorus tends to follow the increase in population up until the early 1990s and the advent of the EU Wastewater Treatment Directive, which resulted in mandating of larger sewage treatment works, introducing tertiary phosphorus treatment and a dramatic reduction in concentrations as a result of that. And because this is a phosphorus community, I thought I'd show you a little bit in more detail about the history of the phosphorus in the River Thames. Concentrations really don't start to ramp up until the early 1960s. And there's a strong annual signal to the phosphorus concentrations, and that annual signal dramatically increases in amplitude in the 1970s, reaching a big peak actually in a drought year of 1976. And if you look at the concentrations there, they're pretty eye-watering. We have concentrations in the River Thames of phosphate going up to around 4 milligrams per litre. Those are huge concentrations. After the early 1990s, as I said, the Urban Wastewater Treatment Directive started to have a big impact on the concentrations, but there were also major changes in the agricultural activities in terms of land management and fertilizer applications that we delve into in more detail in the paper. And when we look at the annual signals, the hydrological drivers really stand out. We see very strong relationships between phosphorus concentration and river flow. And these relationships, the flow dependency, switches quite suddenly during the time series. So in the 1930s, we see an increased concentration with flow, non-point diffuse source phosphorus mobilization. And then in the 1940s, that switches to a dilution. And this relates to the changes in wastewater management at this time. And the point source dilution continues for the rest of the time series. And that change between the 1930s and 1940s really reflects a change from waste being disposed of to land as sewage farms, And in the early part of the 20th century, wastewater treatment plants started to be built, and you see a change whereby the wastewater treatment plants deliver that effluent as a point source, and you start to see those dilution effects. So in total, we see that since the 1980s, there have been big changes in phosphorus in the River Thames. When we calculated the phosphorus loads, there have been huge improvements, reductions in phosphorus loads of about 80%. However, the base flow concentrations of phosphorus in the Thames remain more than zero point 0.2 milligrams per litre. So huge improvements, but there's still an abundance of phosphorus in the River Thames. And of course, we're interested in the phosphorus because of its role in eutrophication and algal blooms. And phytoplankton blooms tend to be the dominant primary producers in the Thames. Now, we have a silica record going back to 1936, along with phosphorus. And silica is really important because diatoms take up silica to form their outer shells. And this results in a negative relationship between chlorophyll and dissolved oxygen silica concentrations. And whereas the chlorophyll data that we have are relatively sparse, we do have, as I say, this really good silica record. And so we can use silica depletion as an indicator of algal blooms. And our silica, so we looked at a concentration threshold of chlorophyll of 100 micrograms per litre, which denotes some of the higher bloom conditions in this part of the River Thames, and identified a threshold silica concentration. And we found that during the time series, we were seeing periods of intense diatom blooms, and some of these particularly occurred between 2005 and 2016. And of course, this was despite the phosphorus loadings having been dramatically reduced at this time to levels that actually hadn't been seen since the 1950s. So despite those big reductions in phosphorus loadings, we continued to see an abundance of diatom blooms. But we
Helen,
also, hello?
yes, Helen, if I may ask just a point of
Yeah, sure.
clarification. So the inverse relationship between silica and
Yes.
chlorophyll, that's because you're measuring silica, free silica in the water column, right? And so,
It's dissolved reactive silica,
right.
yes.
And so as the diatoms take it up into their cells, it's no longer it's no longer free in the water column. And
Yes,
yeah, okay,
yes,
great.
it's assimilation. So that silica depletion is an indicator of diatom blooms, and of course we're interested not only in phosphorus, but how other factors drive eutrophication, including water temperature. And we denote quite a narrow temperature window for diatom blooms in this part of the River Thames. And so we were able to look to see how many days per month where the average daily water temperature in the Thames was optimal for diatom blooms. And we have meteorological records and water temperature historical records. So we could go back and have a look to see how the number of days that were favourable for diatom blooms had changed over the last 150 years. And we also did another analysis to look to see at higher temperatures, which are favourable for cyanobacterial growth, how those conditions had changed over the last 150 years. And what we found was that on average, since the 1960s and 70s, increases in river water temperature have resulted in around 15 more days in March and April for those spring diatom blooms. and around 22 days increase in a number of days in July and August, with water temperatures favourable for cyanobacterial blooms. So, what our results are showing was that water quality management, in many ways, is now treading water in a warming climate. So, reductions in nutrient emissions, whilst really significant, 80% reductions in phosphorus loads, those haven't been sufficient to reduce phosphorus or nitrogen concentrations to limiting levels. There continues to be an overabundance of these nutrients in the river. And meanwhile, warmer temperatures are resulting in an increase in algal bloom potential, with an increasing number of days with favourable temperatures for diatom blooms in spring and for cyanobacterial blooms in summer. And so overall, this water quality data set documents the impacts of 150 years of social, economic, and environmental change. I've touched on a few things in this presentation, but many more details in the paper. But we're looking at through a unique historical record through the lens of river water chemistry and quality. And in many ways, the Thames exemplifies the multiple drivers that are converging to impair river water quality, and the challenges we face in remediation. And this is representative of many rivers around the world, myriad world rivers, subject to intensifying eutrophication pressures. And really, this remarkable 150-year record really highlights the challenges of managing water quality in a warming climate, and also the need to further tighten our phosphorus emissions to control nuisance and increasingly harmful algal blooms. And so I just want to finish. I mentioned at the start that this research is actually having some broader transdisciplinary impact through a really exciting collaboration with the Jacobs School of Music at Indiana University, working with an environmental composer, Timothy Reinholtz. Now, Timothy works through a process called sonification. And what he did was he mapped the data points from 150 years of Thames River water quality. So phosphorus loads, water temperature, chloride, biological oxygen demand, and he mapped those to musical parameters like pitch, rhythm, dynamics, and density, but using musical cells from Handel's water music. And some of you may know that Handel's water music was actually first performed on the River Thames back in 1717 for King George I. And so by integrating this data set into Handel's musical framework, this new piece of music, Echoes of the Thames, is really creating some amazing connections between the environmental history of the river and its cultural heritage, and really helping to widen public engagement around the issues of water quality and environmental change. And I was fortunate to be able to go and in person to hear the Echoes of the Thames having its premiere at Our Hall in Bloomington last month. And wonderful to learn how the world's longest water quality record is now resonating with the audiences way beyond the environmental sciences. So thank you.
That's really excellent, Helen. It's pretty cool that they did that. Just two questions for you. One, when you're talking about these recalcitrant phosphate concentrations, is it your hypothesis that that's due to legacy phosphorus buildup in the sediments, or is it something else?
So it's a combination of factors. Undoubtedly, yes, there is a legacy phosphorus signal to that. You may remember that through the Phosphorus Research Coordination Network a number of years ago, a paper led by Steve Powers, the Thames was actually part of that story, looking at legacy phosphorus accumulation and drawdown. And yes, there is a legacy signal to that. There are also issues within the Thames watershed of issues associated with continued impairment from wastewater discharges. So although great improvements have been made, there continue to be phosphorus discharges from wastewater treatment plants that are continuing to impair concentrations at base flow. So there's a combination of factors there.
Right. And so my other question is there a way to separate out the signal from waters warming from climate change versus thermal pollution? Is that
Now that's an interesting one. So the our water temperature record was actually infilled using the relationships between measured water temperature, air temperature, because we have great air temperature records going back 150 years and beyond. And there were very strong linear relationships between the water temperature and the air temperature. So I think the signal that we're seeing is predominantly linked to climate, but I think there's more work that could be done in relation to looking at disentangling potential impacts more widely on river water temperatures, certainly.
makes sense? Thanks so much. And thanks again for giving this presentation.
You're
Good luck
very
with
welcome.
research.
It's nice to chat with you.
Yeah, take care. Thank you.
Okay, thank you.